come on in a sec. Right, we can write that down. You got that? Principle of moments now. Yeah, okay. Right, so what would happen if equal but opposite forces are applied at the ends? It would rotate. We saw that previously, that's a couple. So it would seem like it shouldn't move, but of course it does, because we were discussing that. So what's the deal? Well, the plank is moving, it is rotating, so a turning force makes it turn. If it's not turning, then it would be in equilibrium. So when we say equilibrium, we mean completely not moving, completely balanced, both up and down, left and right, and clockwise, anti-clockwise turning forces as well. So equilibrium means the total net force is zero. And I should really also say the total net force including turning force. So that means the force to the left equals the force to the right, the force up equals the force down, and the clockwise turning force equals the anti-clockwise turning force. I've gone back to using L. I really want to use tau. Question, Jerry? Bruce is trying to study. Be good. Is Jerry distracting you? Yeah.
I'm teaching.
No, I don't think so. You have nothing to teach Bruce. He knows everything. All right. Continue? No, not yet. Yep. Okay. Continue now. So, the last point is actually known as the principle of moments. That is, the clockwise moments equals the anti-clockwise moments. And in fact, I think that's important enough to write down. So, if you have this turning force should equal this turning force if it's in equilibrium, if it's balanced. This is called the principle of moments, meaning simply the clockwise equals the anti-clockwise turning force. So can you make note of that principle of moments? Basically, it's the last rule here.
Only the last one is the principle.
Yeah, exactly. Only the last one is, yeah. Got that? Yeah? Okay. Okay. So there's not a lot of definitions in this lesson because the last lesson had a lot of definitions. So just a quick recap. What are the other words that mean turning force? Moment and torque. What's the letter that represents turning force? Oh, come on, I've said it. No, I've said it a few times. Tau. Yep. And the formula for turning force, the torque? Force multiplied by distance. And one of those must be perpendicular, either the force or the distance then. Okay. And we don't care about parallel forces because they don't cause a turn-in, since they act through the point, the turning point. Oh yeah, and what's another name? Two synonyms, two other names for turning point? Fulcrum and pivot. So there's lots of vocabulary in the last lesson, okay? Not so much in this lesson. This is more about problems. So we'll have a look now at our first problem. So again, I'll do this one, but I want you to try and draw the picture, and then I'll do it. So you can either write or draw, or both. So write this or draw this, and I'll do the answer. You know seesaw? Yeah? Okay. You have this? Yeah? Okay. So let me do it now. Firstly, the seesaw is 100 kilograms. So it's a heavy seesaw. We'll draw it like this. So this is 100 kg. So the picture looks like this. And you have the boy here and the girl here, and he is 40 and she is 30. So that means there's a force here of 40g and a force here of 30g. Now, is this in equilibrium? No. Which way will it rotate? It will rotate anti-clockwise. It will rotate this way. Okay, so we want to know where should we move the pivot so that it's balanced. So for example, at the moment it's in the center, and this is no good because it's not balanced. So the father would like to move it. Should he move it to the left or should he move it to the right? To the left. Because we would like the turning force from the boy. Yeah, so that's the force multiplied by the distance. That should equal the turning force provided by the weight now, because it's not balanced, and also by the girl's weight. So you have one force turning it anti-clockwise, but you have these two turning it clockwise. So let's calculate the total turning force anti-clockwise. That would be 40g, and we don't know this distance, we'll call it x. Now, we know the distance from here to here. What is it? Oh no, 2.5. And here to here? 2.5. So, if here to here is x, his turning force will be 40gx. Okay? Now, that's the only anti-clockwise force. The next one are the clockwise force, and we have two of them. The first one is this one here, which I drew. This is going to try and make the seesaw turn this way. So what is the force? 100g. And the distance, be careful, yeah, 2.5 minus x. Plus, the girl will also turn the seesaw clockwise. What's that distance? 2.5. And the force? 30g. So the principle of moments says that the two should be equal. So the principle of moments say that 40gx should equal 100g 2.5 minus x plus 2.5 30g. So this will have all the g's cancelling. We'll get 40x equals 250 minus 100x plus 60, 75. So that means 140x equals 325. So that's 2 and then 80, 45 over 49 over 9 over 28. 2 and 9 28. What's that? 2 point. No, it couldn't be 0.43. It has to be 2 point something.
2.32.
So that means the father had to move it a little bit to the left. How much did he have to move it to the left? Well, if x is 2.32, then this distance is 18 centimeters. Yeah, so the father had to move it 18 centimeters towards the boy to balance it. So what's happening here is, in the original picture, why do we not care about the weight of the seesaw in the original picture? Yeah, because the weight is at the pivot, it means we don't care about this. When the father moves the pivot to the left, it basically adds in an extra turning force that allows it to cancel the boys. Okay, so write this one down, please. We'll have some more examples to do. This would be a typical section A question in the exam.
So after the father places the boy can only stay to the left and use that position.
Yeah, when he moves it 18 centimeters to the left, the seesaw will be balanced now between the boy and the girl.
Which they cannot change, right?
Correct, they can't change. It has to be 18 centimeters towards the boy. Okay, you got that? KJ, can I continue, or you need to write the... Bruce? Yeah.
The seesaw is 100 kilograms.
Yes.
And if we move to that, we consider the whole 100 kilograms to right side.
Yeah.
Only one side.
Yeah. Yeah. The center of gravity is the single point in which the weight acts for the whole object. So it's just the right side, because it's still the center. Now there's actually a force that I haven't drawn in the picture, but I don't really care about it. Which force is missing from my picture here? Not friction and not drag.
Reaction.
Reaction. Where? At the pivot. Because if there was no force here, all three would fall down to earth. Right? Yeah. Now, why did I say I don't care about this? It's at the pivot, so there's no turning effect from it. Yeah. Okay. Here is another one, and this is a very common exam question. So again, you can write or draw, and I'll do it. You have a 100-gram meter stick. Bruce, Jerry, do you know this word, suspended? Jerry, do you know this word? No, it means hanging. Hang. H-A-N-G. Hang, yeah.
I know that.
Huh?
What is meter?
What's a meter stick? It's a
1
stick
1 meter.
that is 1 meter long. And you use it to measure things up to 1 meter in length. So you can write or you can draw. Okay, I see we have a couple of pictures here. Lee, Monica, you have them drawn?
Yeah.
Let's see what you have there. Yeah, that's the right idea. Yep, that's it. Bruce, did you draw it? Okay, that's fine. And Jerry? Did you write or did you draw?
I draw, but I didn't finish it.
That's okay. Show me what you have.
But that really not, isn't like this like that.
No.
No?
No. Good try. Let me draw it for you. Okay, so we have a meter stick, meaning it's 1 meter long. So here is 50 centimeter mark. Here is 25 centimeter mark. And then here is 90 centimeter mark. And because it's 100 grams, it means there's a force here of 0.1 G. And this is hanging from 2 strings. One here and one here. And we'll call these forces T and S. And I want to find the T and the S. So, because it's in equilibrium, we know that T plus S equals 0.1 G. Right? But what's the problem with this? Well, it's not enough. I need another equation. So because it's not moving, we can also say what? Yeah, well, what's this called?
Moment.
Principle of moments. Yeah, that the clockwise turning force equals the anti-clockwise. Now here's the key question. Where is the pivot?
T and S.
Alright, can I pick one?
Only one.
There's only one pivot.
S.
No, you're not sounding convinced.
It moves like this.
But why not T? For the same reason. Because reasons. Any others?
T moves like 0.
Yeah, where? So you're on with 0.25?
Equal.
I know, but I want to know where is the pivot? Where's the turning point? You're going with 0.25? Okay? No.
Half of.
You're going with 0.5? 50 centimeters? You changed your mind? Okay, you're going with 50 centimeters as well. Lee, you're going with
25.
25, okay. Anyone else? Right, now you're changing your mind.
50.
Yeah. You're going with now, which one? Okay, fine, you're going with that one. Bruce? No? KJ?
30.
You're going with 35, okay. Brian? Where's the turning point? Where would you like it? 90. Okay, you're going with Lee then. Andrew? I know you have to pick one.
75.
You got 25. Khaled? Got 25. Okay, the correct answer is...
9.
5.75.
No! What?
5.75.
You're going with which one?
5.75.
5.75. Okay.
No, I think 50.75.
Okay.
57.5.
57.5. Okay. The,
I'm just between
Yeah?
it's 25.
okay. The correct answer is
9.
no. All are right. Yes. If you choose the turning point to be anywhere you want for a system in equilibrium, you'll always get the same answer. Okay? So what I'm going to do to prove this is I'm going to do this question twice. The first time I do it, I'm going to put the turning point here. And the second time I do it, I'm going to put the turning point here. To show you, I'll get the same answer. Okay, so firstly, this one here. What is the... Let me just open up the calculator here as well. Right, this force here, clockwise or anti-clockwise compared to here? Clockwise. And this one? Anti-clockwise. So, yeah, because it's making it turn that way. Right, so what is this turning force here? The first one. 0.25, this distance, times 0.1 g. And that should equal this one. And what's this distance here to here? Is it? Because this here is a 40, isn't it? And that's a 25. So yeah, 65. Times S. So can we get S now? We can. So can someone just type in 0.25 times 0.1 times G over 0.65. Actually, I have the calculator here too. 0.25 times 0.1 times 9.81 divided by 0.65. 0.377 newtons. And then I can put that back in to get the T. So the T will be 0.604 newtons. So these are the two forces here for this problem. Now when you write that down, I'm going to remove this and do it again, but have the turning point in a different place. Did you write this down, Bruce? You're thinking. Maybe you could write it down and then think.
When we are doing the MT and clockwise thing,
Yeah.
we no need to consider the T, because T is doing the MT clockwise.
No, the T passes through the turning point in my picture. So it has no turning effect. Yeah. Can I remove this? Did you have the answers written down? Yeah? Okay. Let's do this again. But this time with a different turning point, a different pivot. So now I'm going to put the pivot... Oh, I've run out undo. I'm going to place the pivot here. Okay, so if I place it here, this one, clockwise or anti-clockwise? Anti-clockwise, it's making it turn that way. This one, clockwise, it's making it turn that way. And this one, anti-clockwise, making it turn that way. So let's do the clockwise ones first. What is this distance here? Yeah, 0.5 times 0.1 g. And that must equal this one. What's this distance? 25, isn't it? T plus, and then this one 20. Oh, well, that's obvious. That's 90. S. Yeah. So now you get 0.25 t plus 0.9 s equals. Let me write that again. 0.25 t plus 0.9 s equals 0.05 g, if I keep the g in it there. Yeah, you're giving it to me as the decimal? That'd be great. What is it as a decimal, please? 0.49? 0.49. 0.5. And then this one here, 0.1 g, is 0.981. Now you have two equations here, and you would have to solve them. What would you multiply this by to solve? If I want to cancel the t. 0.25. Or you could multiply this one by 4. Because what will that make at the start? A t, which then you can cancel them. Yeah? Okay, so you know how to solve this from math class. Let's take a shortcut and use the calculator. Mode 51. 1. And let's see, do we get the same answer? So my first answer will be t. What was my t in the last? Ta-da! And then the same answer, even though we use a different turning point. We're allowed to do this if it's an equilibrium. Because if it's an equilibrium, there isn't really one special turning point. Okay, so I'd like you to write this one down as sort of a second way of doing it. But this way is a little bit harder if I did it this way. Why? Yeah, I have two equations, whereas last time I only had one equation and one easy equation. So if you can choose the turning point, you should choose it through one of the unknowns, through one of the variables. Yeah, did you write this down? Yeah, okay. I can close this, yeah. Andrew? Are you sure? Okay. Two men, identical twins, are just about able to carry 50 kilograms of a non-uniform beam of steel. The beam is 4.6 long. The first man is 10 from the end of the beam. The center of gravity is 2.1. Yeah. Do you know, I don't really think we need to do this one because it's quite similar to the other examples we're doing. It's very similar to the first example I did with the seesaw, where the father has to move the pivot. The only difference here is you have to move where one of the forces is. But I don't think there's much value in this. I'd rather actually have you try some of the homeworks because you have two worksheets here. So we won't worry about that example. So you have two now. The first one is the center of gravity, which is quite easy. And the second one is from this lesson, which is the principle of moments. And yeah, I don't think these are too difficult. So you can start these now. Oh my goodness, Brian. You had cookies and you didn't tell me. I am so shocked. So shocked. Yes? Oh, thank you.
Wow. I'm all in.
I love
No,
that.
only for me.
I'm feeling too.
Wish. Okay. Thank you, Brian. I hope I'm not eating your lunch. No, it's a snack, yeah?
I'm poor food.
Yeah, I don't want you to ring your mother and say, my physics teacher, she keeps all my food. I'm so hungry. I don't know what to do.
I can help you. Kill me. I can help you.
No, she doesn't need help.
I need.
You need one, okay. There you go.
It tastes good.
That's good. It tastes better because it was free.